That's even better. Good job. Okay, so this work was done in collaboration between several universities, but also industry, Oracle. My name is Marina Shimchenko, and there was another PhD student working on this project equally, Sanaz Tavakolisomeh, who is unfortunately, she couldn't come. I also would like to thank Google and ICM for Women for sponsoring my trip here. Now, when formalities are behind us, let me tell you a little bit about heap sizes. Okay, so I hope you all know that when you run a Java program, you also need to set the maximum memory size, or rather, your Java needs to know how much memory you're using, otherwise it's not going to function. And it is a super important parameter. So this research that I link down here, it's also our closest related work. Among other things, they looked into correlation between execution time and memory. And what they found is this parabola-like dependencies. So if you have not enough memory and very frequent GCs, it's not good for your performance. But if you have too much memory and infrequent GCs, it's not good for your performance either. So hopefully we want to stay somewhere in the middle here. However, setting up a memory, a heap size is a struggle. There are a couple of things you can do about it. You can go with the automatic approach, and your GVM will give you 25% of the available RAM on your machine. You can imagine that it's definitely too much for a hello world program. At the same time, your program can crash if it's not enough. And your alternative is to set up memory heap size manually. So this little study, they looked into different GitHub repositories to see what method people use the most when they set up a heap size, and it turns out that they go with the powers of 2. What they also found is that it's very common for people to make mistakes. For example, in almost 3% cases, instead of 8,192 megabytes, because of a simple typo, programmers gave their programs more than 8 times less memory. It just showcases that as end users, we are not very good at setting up this parameter. And no wonder, there are no guidelines. Okay, but maybe, if you spend an eternity and actually find your perfect heap size, maybe it's gonna, you can keep it forever. Well, unfortunately, not really, because the heap size varies also with your hardware. So we did this tiny experiment where we ran 4 benchmarks, Tomcat, Sprint, Batik, and Luindex on 5 different machines, and here I sorted them by the size in terms of their cores and how many threads they use, from the smallest one to the biggest one. And let's look at the numbers. For example, for Tomcat, you can see a very clear pattern. So the memory just grows with the number of cores and threads. If we look at Sprint, for example, it's kind of a similar pattern. So the heap size grows, but you can also see that we need as much memory for the 4th machine as for the 1st. Okay, it already breaks the pattern, but let's go on. Batik, well, you can see that for the 2nd machine, you need twice as more memory than for the biggest machines. And then after the 2nd one, it stays relatively the same, and the same goes for Luindex. So here, you have multiple different applications. They have absolutely, not consistent pattern of how they change heap size with the hardware. So it's not even possible for you to predict it. Okay, that's not good. What do we propose? We propose to go from setting up memory, how it is now, to setting up GC CPU overhead. So GC CPU overhead, it's pretty much the resources of your CPU that you're willing to spend on your garbage collection. Why is it even possible to go from memory to CPU? Well, there is a link between the two, and this link is GC. So let me try to give you an intuition behind it with this simple infographic. So right now, we're setting up memory, right? So more memory you have, less GC you need to do, and the other way around with less memory. But GC, in turn, it's actually your CPU, right? So more GC you do, more CPU resources you need to spend doing GC. So we can actually control either memory or CPU. Why is it good? Why is it better to set up GC CPU overhead? You can imagine a black box Java program that you need to run as a service. You have absolutely no idea how much memory it uses. You didn't develop it, but yet Java requires you to set up a maximum memory capacity. Well, that's not going to work. However, with CPU, it's easier for you to reason how much is actually reasonable for GC to spend, right? And another example would be this program with varying memory usage or varying allocation rate. So for example, let's say that in the beginning it uses a lot of memory, and then of course you have to set up your memory quite high, right? But then the rest, all of this, it's a waste of memory. It's definitely too much memory. So you're gonna end up on the right side of this parabola dependency, right? We'd rather have something like this, and I'll give you an indication how we can actually achieve this with the CPU control. So let's look at it how it was before. So before we have fixed memory, and then because allocation rate varies, GC will vary too, and because GC translates to CPU, then your CPU will vary as well. So both the white and the green lines, they go together. Now let's say we actually fix CPU. What's going to happen with GC and memory? Let's say we have this much memory. I know it's a little bit confusing to have them all on the same scale, but bear with me. Let's say we have this much memory, and this is the current CPU, GC CPU overhead. How do I calculate it? Using this super simple formula, time that you spend on GC divided by the time that you spend on application. This is your current GC CPU overhead. And let's say, so here, we definitely underperform. The target is here. We want it to be here. So what we can do to go there is to adjust the memory. So in this case, we can decrease the memory to increase the pressure on CPU. But what happened? We overshoot. That's okay. On the next cycle, we can adjust it again, and hopefully, eventually, we will be together with a fixed CPU rate. And now, one thing that you can see is that memory varies instead. So before it was CPU that was varying, and now it's memory. Why now? You might have a question if it's a new idea. Well, it's actually not, but it was done in a different context. So before, we dealt mostly with stop-the-world collectors, and your stop-the-world collectors, it means that you run your GC while application stops completely. This is your stop-the-world pause, right? In this particular setting, we want to finish GC as fast as possible. So there is absolutely no reason to divide CPU resources between application and GC threads. Otherwise, if you prolong this GC cycle, it just affects your throughput. But this is not the context that we are dealing with now. Now, fully concurrent collectors emerged, and one of these collectors being ZGC, for example. In fully concurrent collectors, you have GC threads running in parallel with the application, meaning that GC is not on a critical path. And if you don't like listening to my voice, you can also read this. So GC is not on a critical path. Therefore, we can actually play with the frequency, play with the duration, and not affect performance. And by performance, in fully concurrent collectors, I actually mean latency. Okay, so we did some experiments. We used the Sandy Bridge machine, 32 cores. You can read the stats. We used 2 benchmarks, and we implemented it in a generational ZGC. Let's look at the results. Let me show you super complicated graphs that everybody loves. So here you can see, this is vanilla ZGC, right? So vanilla ZGC, it's basically ZGC without changes. This is how it was before. Here you can see the heap capacity, or the maximum memory size or heap size was set to 32 gigabytes, which is, we just followed this methodology of giving it the power of 2. You can also see the time in blue before GC and memory in orange after GC. So pretty much your program doesn't really need a lot of memory, right? But yet at some point the program used the whole capacity. You gave it 32 gigabytes, it used 32 gigabytes. Okay, now let's look at it how it's now with our implementation. So this is our implementation with GC CPU overhead equals 1%. And let me just point to a couple of differences in the two graphs. So the first one being that suddenly the green line is not straight anymore, it adapts. So your memory varies, right? In the beginning, we start with a really tiny heap size, and then because there is a lot of pressure on GC, we have to increase the memory until the point where we actually can satisfy the target of 1%. Another thing that you barely see, but let me tell you, so here we have maximum of 800 megabytes of memory, while before we had 32 gigabytes. So here we use a lot less. But because we use a lot less memory, we have to run GC way more frequently. So that's why you have this a lot of blue lines here. Perfect. Now, we actually in the paper evaluated a couple of different GC overheads. First of all, because we wanted just to showcase that it works. And second of all, we were thinking about maybe we can find a good range that we can recommend to the users to make it even simpler for them to set up a GC CPU overhead. So we looked at 5, 10, 15, and 20%. There is nothing that prevents you to go above this. We didn't do it in the paper because ZGC, again, it's a low latency collector. So we think that there is absolutely no point to run it with more than 20% because it might affect latency. But again, you can do it. We didn't. Now, we looked at multiple parameters like time, memory. We also looked into energy and latency, of course. And energy results you can find in the paper. Latency, I'll just briefly mention. Let's first look at the execution time. Here we normalize everything to configurations where we set heap size manually following powers of 2. And you can see here that, okay, at first, if you don't give enough space to your GC, performance drops, and then we even gain a little bit performance, then we gain a little bit more, and then we start slowing down the gains. So here, it's almost like the parabola that I showed you in the beginning. So we basically concluded that if you optimize for execution time, at least for our benchmarks on our system, a good range seemed to be from 10 to 20%. Memory just follows a very nice pattern. It just goes down, 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 down. And it makes sense because more resources you give to your GC, more often you can clean your memory, therefore less memory you need to use. And here, if you optimize for memory, you can go with really high GC CPU overheads. So if you optimize for execution time, it seems that this range is good. It is very similar to energy because for ZGC specifically, there is a very high correlation between execution time and energy. Now latency. Latency is actually the most important for ZGC and latency-oriented collectors. We didn't find any statistical significant results that could prove that latency got hurt. We actually found positive patterns, but latency measurements in the capo vary so much that it's very hard to prove anything. So you can read the paper, we just basically conclude that, you know, it seems okay, but statistically, unfortunately, we cannot prove anything by now. Okay, so in conclusions, we believe that GC CPU overhead is more intuitive to set up. And a good thing about it is that it's not going to vary with hardware, right? You can just transfer the same percentage to your other configurations on other machines. We also showcased the possible implementation of this technique in the context of a fully concurrent collector. And what's even more important, that we found a preliminary acceptable range where performance metrics do not drop. And by performance metrics, I mean latency. Okay, and now back to the beginning. Questions? and I'm looking for a job.
Do we have any questions?
So with a generational GC, where there's like a choice over which part of the collector runs, is there some way you could use this kind of technique there? Because it's sort of like, which part of a collector runs seems sort of, that's trained by like different sizes.
Yeah, so what we do, you can think about different generations as different cycles. So every time a collection runs, we just measure how much time you spent on your GC, how much time you spent on your application, and if it's below or above the target, we adjust the memory. So it doesn't really matter. You can totally implement it in a non-generational world. It's the same principle.
Thank you.
Hi, thank you. The optimal range that you found, is that not dependent on the memory allocation profile of the application in question?
So that's the beauty of it. If you set up memory size, you have to deal with allocation rate, right? And different patterns of how your application behaves. With CPU rate, the only thing you care about is just how much resources you're willing to spend on your GC, and then memory will adapt. So depending on your allocation rate, we will just adapt. The adoption rate will be not maybe as fast as you like it to be. So for example, if there are a lot of changes in allocation rate along the application, we might be always a little bit off from the target. But if your allocation stabilizes at some point, we will get quite close to the actual memory usage of your application.
Okay. Do I have time for one more question? You also took a look at different hardware and their implication on the memory size. Did you look at different hardware with different percentage of GC targeting as well?
Well, in the paper, there is only one type of hardware. However, we did look at multiple hardwares, and in order to integrate it in OpenJDK, where we aim to integrate it, we will need to do more. I think it's an indication that we need to wrap it up. Okay, so yes, we need to do more experiments with different hardwares and also different operating systems.
Thank you.
All right, thank you everyone. Can the speaker again?